Today to talk about Hadoop, an area that I'm pretty excited about, and in fact is very relevant and important right now in the space of Colorado, Denver, Colorado, USA, where I live and work. There's a lot of companies right now that are in the startup mode, and we often know that means a lot of head out to those delicious bookmarks. I'll have the links on the slides that can be downloaded from the conference. So we're here to talk about this product, Hadoop. What is this thing? Where did this name come from? And it actually is a product that came from a derived tool. Anybody recognize this face? Shout it out if you know him. Exactly, Cutting. Doug Cutting from Yahoo. So this was his origins. He's now at another company we'll mention towards the end of the slides. But he was one of the authors on the Lucene project. And all of this heavy search and heavy calculation, heavy indexing work came from those very foundations of Lucene. Now, the interesting thing is the shift, the thing that's made Hadoop very important these days is actually in the hardware space. And that's a little bit of a head scratcher here for a second. Really? Hardware? How is hardware affecting a software product that we're here to talk about today? And quoting a friend of mine, Brian Getz, the era of clock speed increase is over. If you look at the graph of where we've been with clock speeds in the last couple of years, we've stopped. It's frozen. This is a problem. We need a new way to keep achieving greater and greater scale and speed, but it's not happening with just increasing the count of the clock speed of the transistors that we have today in the CPUs. In fact, I'll go out on a limb, and I have a couple of my colleagues even here that will agree with this statement. It is absolutely possible that the CPU you have in your notebook, in your desktop that you have today, may be close or at the fastest clock speed you'll ever have in the rest of your career. We are coming close to the hardware limits of what we can do with transistors. So, what do we do to solve this problem? Is a fundamental change of how we do computing. What are we going to shift here? We are going to go to a parallel model. You've already seen that with the multiple cores that we have today, multiple cores inside a single CPU, the hyper-threading that we've done for the past couple of years. But this idea is escaping the single processor in the single space there. We're going to the same idea on a grid computing level. And you say, oh, grid computing, that's old. I've heard about that from vendors for the last couple of years. But there's a couple of things that this has dramatically changed over the vendor solutions that you've heard for, say, the last even 5, maybe 10 years. Now, the first thing is a strong capability to operate on MapReduce concepts. You're going to hear this word a lot. It's gotten a lot of buzz from various different companies. It's not singled out just to Hadoop. So it's great if we have a foundation for just a minute as to what MapReduce does for us. So straight into the technology here. This idea of MapReduce, its formal, tangible sense, came from Google. You're going to find some very strange blending of the names and branding behind some of these technology concepts. The paper came out from Google, 2004, it was published, on how they were using MapReduce to solve some of the really big, really hard problems. Now, the funny thing is they don't often give away source code. This wasn't actually a formal implementation. This was actually just a description of the process and the techniques to get there. But of course, somebody crafty, a lot of people can contribute to a project. Doug Cutting took this idea and mapped it onto an application framework that we can use today. The part from this paper, it's about 14 pages long, and if you're serious about getting into distributed computing, it is a must-read paper. I've got the link at the back of my slide decks. All my research is at the back, so you can follow all these papers. But very important takeaway from this, if I were to boil it down to just the very narrow thing that you care about, I would mark that as being a distributed programming model for very large data. Now, some of you may get up and leave the room because you say, I don't have large data. We kind of deal with smaller applications. Thank you very much for giving this presentation. But I will say, hold on, and let me see if I can change your mind over the course of this presentation that just because you don't have large data today, maybe you're just missing out on saving some things that you might need to save and process later. So just because you don't have big data right this minute, don't walk out on the talk. I'm going to try to change your mind on that. Now, the origins of MapReduce itself in the Hadoop form came from the Nutch project. It was a derivative, a sub-project of Lucene, the search engine from Apache. So it was one of these things kind of like Maven, another thing that I'm a big speaker and fan of. It came out of another project Somebody liked the idea, it kind of distilled and became its own standalone project. That's exactly where Hadoop came from. It still has strong ties back to the Lucene and Nutch spaces. It is one MapReduce implementation, though, just one. There are many others out there, commercial and open source. But it has some strengths across the ecosystem that the other implementations just can't yet compete with. It was founded by Yahoo, which is the first head-scratcher about that paper. I just told you the paper was Google's writing, and now I told you the implementation was Yahoo. Absolutely, we've got all this kind of cross-pollination happening, and I think it's kind of exciting to see that it's a competition happening between the barriers of these otherwise strongly competing companies. And it's all open source at Apache. That's the third leg that's pretty important to me. Having contributed to some projects at Apache and so on, I like the fact that it's open and independent. It's not linked into someplace at Yahoo, someplace at Google. It's nice and off on its own. We know it'll have some longevity besides these companies' life cycles as corporations. So the list of companies that are using it, the next thing that's important to me when I'm taking something like this big of a sea change to a new company, they say, well, I need referenceable accounts that I can say are already using this. I have never seen a who's who page like the who's using it on Hadoop. It's growing. It's a wiki page, and it's growing literally daily. Look at the edits on this page. It's so long, I couldn't scroll through it in the rest of this talk. But some of the grids that are in use on this are mind-blowing. Look at the numbers here in the middle on this. 100,000 CPUs on a 25,000 node grid. If you have needs bigger than that with the problem that you're working on right now, wow. Everyone I know that I've worked with is under this number. So it's already, someone's proving that top edge for you so that you're not even having to stretch the boundary of what it's capable of doing. Now let's put some formal knowledge around what MapReduce is. I've got some diagrams and descriptions. I'm going to try to help you understand the foundation of Hadoop and the MapReduce concepts. But then we're going to add a few exciting other pieces that the Hadoop ecosystem brings to the table. Now there's three main steps to a MapReduce process. And the interesting thing is, you actually are only responsible for authoring two of these. The two steps that you author as a programmer, as a developer, are the map and the reduce. And for some of the common implementations, amazingly enough, you can actually use one of the implementations for map or reduce that may already exist. So this isn't even guaranteed that you have to write those, but the framework handles the middle part. You're authoring the top and the bottom, the map and reduce. Now, in mathematical terms, we're taking a map, data structure as you know it, transforming it to a list. K1, V1, K2, V2. What does that imply in the mathematical sense? Just shout out at me. I've been promised you a really smart audience. Map to list. What do you think of on that transformation? What's the first thing that comes to mind? Index-based. Order now matters. And something you might guess that applies to that is a reduction in the size of the list. I know it's not implicitly stated there, but you might assume that the size of the map is reduced, and it is. You've got a smaller list as the output. You start with the set of data at the very beginning. Now, that's a function that you write. And someone asked the other day, in all seriousness, and I tried to hold a very straight face with this, where's the framework that helps automate writing the maps? And I said, it's right in here. That's the hard part. That's why we still get paid to write software. If that were automatic, there'd be nothing to talk about. This is hard. This is very hard to do. But the next piece, shuffle, moves the data to a correct location, kind of groups it so that it's going to be optimized for the next round of processing. Reduce is then aiming to write the final output. Now, I'm not much of a text or a formal person. A diagram really does so much better for me. So let's see if this helps add another layer of meaning to it. We've got this collection of documents, audio files, anything that we need to do massive processing on. And we have the hard task of trying to figure out how to split it up. We do need to divide the problem into very small steps. Again, there's no magic for actually dividing the problem. Is that breaking it into document by document? Is that splitting it into 10 meg chunks with things that we can handle? This is something that as a developer, you're going to have to figure out what is our dividing line? What are some natural fault lines that this data tends to fall apart on? So that split process typically ends up with a large directory of documents. We're going to use a very tangible example here. We're going to use the document model. We've got little text files or MS Word documents, RTFs, doesn't matter. We've got them sitting out in a massive directory, millions of these things. Next, we're going to run it through a map function. And we can actually have iterative map functions. It's not limited to just one. You could run as many passes on map as you want. But the idea is to write a very small bit of code that determines what is interesting and what's not. So what might you author in the terms of a map function? You might say, oh, this isn't authored by a person that I care about. Throw it away. It's out of the data set. This does not have a word that I'm interested in the body of the document. Throw it out. I'm not interested. Oh, this looks like it's too old based on a file stamp. Throw it out. Not considering it. So the idea here is to try to use some small functions, some small decision points to reduce how many things you want to look at. Now, I'm not using the word reduce in the mathematical sense. Eliminate might be a better choice of words. We're trying to narrow the set to a smaller set of documents for the next step. We're putting this into the grid processing network, and then we've marked what the key and the value are for each of the items that we've kept. In terms of a document, that might very well be the file name for the key, and the body, the blob, being the data for it. It could also be in terms of colors. It could be an RGB value, and then every place that that's used in a grid of pictures. It could be a specific word that we're looking for in every other case in the bodies that it exists, but it doesn't care. As long as there's a key and a value, again, it's up to you as the developer. That's the interesting, flexible part about this framework. Now, the shuffle makes your key have meaning, though. It physically moves the embodiment of the documents that share the same key. So if we were using, for example, a word as the key, it's going to move all the same documents that contain that word as the key to the entry to the same physical locations on the grid. And this is an optimization that, again, the framework is handling. If it can do a comparator on your key, it will move the data automatically. And finally, we have the idea of reduce, to produce a useful human output of all of these locations. So it's kind of like a collation process at the very end. Now, that was an intangible kind of hand-waving big picture. But let's turn it into something tangible here in just a minute. I'm going to go through a very precise example on those same steps, and I think it'll be extremely concrete. But you're going to already notice, if you've been to any talks or read any papers or books on functional programming, that this looks a lot like, you're hearing little twinges in my statements that sound like functional programming. And that's absolutely true. In fact, if I went back to this diagram one more time, each of these outputs, each of these layers is a new set of outputs being written. It is not modifying any of the existing files that are already there. It's writing a new set of files to disk, a new set of values. So the originals stay intact. We're writing out new values for each of these steps, or at least new pointers to the existing values. And that's really a lot of what functional programming is about, immutable data structures. So with that in place, go with that functional programming idea and also say that we're writing very small transforms to the data at each of these different steps. Now, I promised you an actual example. We're going to do a word counting example here. And I think this one is, for me, the one that just made it sink in absolutely and clear, crystal clear once I went through this. Word counting. What are we going to do? We want to do an occurrence count of words across a large quantity of documents. Now, you might say, that sounds trivially simple. I wrote that in my bachelor's degree, or we had some example like this in my college book era. But the difference here, and the thing that I ask people to stretch their minds is, for anything that you say you know how to do this on 100 documents, or 1,000 documents, you were really good in school, or maybe even 10,000, you were an impressive A student. What if I asked you to do the same thing to 1 billion documents? You'd say, oh, wow, you know, I wasn't that good in school. And the difference would be that with Hadoop, it doesn't matter. If you can write a good function that can sort 10, that same function is absolutely capable of operating on 1 billion documents. And that, I think, is the magical transformation of how you write code. Write it well for the 10, have it work for the 10 billion on the upper end. And there are practical implementations searching through literally billions of rows, billions of documents. So going with this example, I've got 3 documents here. That makes it tangible for the sake of the example. We got 3 different ones, and we've got some text in each of these. We want to do that word count example. Here's the raw data, and the map is actually going to help us divide it into individual words. The map is going to say, oh, I care about this document because the file stamp is new enough that I'm interested in it. And by the way, I'll help the next step as part of the map function by writing out individual words to disk. Now you say, that sounds extremely inefficient. But keep in mind that MapReduce and a Hadoop framework has some giveaways for the fact of the scalability. We make a little bit of a compromise. Think again, you can't load 10 billion documents into memory, so we have to make some trade-offs in terms of being a little inefficient on the small scale for some massive scalability efficiencies. This is not a free ride. This is a trade between a couple of different things. So we split these words into pieces, writing them back out to the file system, and in this particular case, we could actually have the key and the value be exactly the same. There's nothing that prevents that. The key could be the word. The value could be the word. The key could be the word. The value could be a 1 for a single occurrence of it. And that works perfectly for this example. The next thing is the shuffle. So if the key was the word, then we're going to physically relocate the documents, or the snippets in this particular case, to cohesive sets of servers that all share that same word. So we're moving all the 4s to a given server. We're moving all the olds to a given server. We're physically moving the data in this case to optimize for the next step. Now the neat part here is we're only moving little bits at a time. So it's nice from a retry standpoint, from an efficiency standpoint. We can move these around relatively simply and pause at any point. And then we run a simple iterator. Again, remembering this is going to happen once per server. We're going to iterate through and count up how many of those words are on disk. And you say, again, this seems like the most naive implementation possible. But think what we've done here. We've made it durable because we've got a lot of little tiny incremental steps that we've written to disk. 2, we've made it very scalable because at any point in time, we are only looking at a tiny little subset of the total data. Once again, making a trade-off in terms of efficiency for that same reason. And finally, if we wanted to sort the output, because remember, it's not guaranteed to be sorted. It used the key as the comparator. It put them on physically co-located servers. But hey, we got the count of the words. Might be great to have it in an alphabetical form or a numerical count order form. That'd be more human consumable. We might be able to reduce again. So map and reduce phases are not necessarily one pass. You can just loop one reduce back onto another reduce. And the last reduce of this pass was to, again, sort these in an alphabetical order. A sort is a valid reduce function. So small functional programming ideas, one little step at a time. Now running this in a directory, I've got a set of log files here from my actual website, so trying to make it very tangible. I've got about 200 meg of log files, just standard Apache output at this point. And I want to say, I want to find all the files that are traditionally file named A through Z .html. I don't care about the dynamic frameworks. I want to see of the standard static pages, what were people accessing on my site over the last couple of months. Now that sounds like something that you could again do with a local grep or a local tool. But remember that the log files, yes, I have a couple hundred meg worth of log files in this example that I just gave. But what if you're Facebook and you have gigabytes, in fact, terabytes of these traditional Apache logs? This problem now becomes a lot harder if you think you're crafty enough to write this. The difference is I wrote this once for my small 200 meg file, and it scales perfectly well with no changes to gigabytes of log files. That's the part that should impress you. That's really neat. No change to the code whatsoever. So let's look at the code behind this. First off, there's grep.java. There's a couple of interfaces that Hadoop provides. It's a Java-based framework, and we're going to use this interface. In this particular case, we're going to implement a tool. And this is something that we can invoke from the command line. Now, some can be programmatically accessed. They don't have to just be from the command line. But this one is literally like the grep that you'd run on any flavor of Unix today. You notice that it has a couple of inputs here, an input dir, an output dir, regex. No big surprise there. Input and output, though, kind of interesting, and it's going to write to a file system. The regex is the traditional one you know. And in fact, as we go down the rest of the body of this function, it's going to become pretty clear that it's very linear, simple steps to coding. We've got a path. We're setting up a temp directory for all of this to be worked on. And you notice that it's using its own classes for path. This is an abstraction so that it can be either a virtual file system that spans large quantities of servers or your local file system if you want to run a simple pass on it. Again, we've disconnected the scalability from the implementation. We haven't had to know that we're on a local file system or this uber scalable one that Hadoop provides. After that, we're going to set up a job conf being the primary class that we use to do that. That's kind of the container to wrap a step in Hadoop. And then we're actually going to use a mapper, regex mapper. I'm going to show you the contents of that in just about 30 seconds. So there's our class that's doing the mapping. We can set a few other configuration parameters up at that point. And then we have a reducer, a summing reducer. And in fact, we got that one for free from the Hadoop framework. So a lot of the common things that you would do already have map and reduce implementations. Granted, for crafty new software you're going to write one of your own. But there's a good set of ones already available. You're not just left on your own to your own devices. Then we've got an output directory. Where is it going to output these intermediate files? Just through that document sample that we just gave a minute ago. I'm going to fire that off and run the job. Grinding out on the grid. I don't see where I specified an IP address or a name of a server. I didn't tell it how many to go work against. I didn't tell it how much file space to allocate or how much memory I needed on each server. So do we have big servers or small ones? I don't see any of that anywhere. Exactly. You don't have that in the code. That's an amazing step. Now we're going to run a second job against here to do the ordering. Just as in the document sample, we can run another reduce process to give ourselves order from the word count. So we can do it in small little steps, writing intermediate files in between, coming back with another pass to achieve something a little bit more usable each and every step here. We've got another job conf we're setting up. We're giving it a friendly name of grep sort. You can see this running out on the network if there's some observation tools to actually see the jobs that are currently running. We're going to set a mapper class of inverse mapper. We're going to flip the keys and the values at this point. We're going to set the number of reduced tasks to 1, though. This is a little bit puzzling. There is still the fundamental bottleneck in some cases where if you want something alphabetized across a large system like this, at some final point to write that one final file that you care about, you may need to set the number of simultaneous threads, if you will, to 1 to get a nicely sequenced and ordered file at the end. So it's not perfect, it's not without some bottlenecks, but it still scales very well for the rest of the hard work of the job. We've got a comparator at the end. We've got a file system that we can write it out to. And ultimately, it behaves like the grep you would know and love, except we actually write a file to disk. Now, what's in that regex mapper? Here's kind of a view into the internals of this piece. And I think this one's relevant to the discussion as well. Simple interface yet again. And here is where the functional programming paradigm comes absolutely into play. Look at the simplicity of map. There's hardly anything to this. When you think about what we're doing on a grand scale, we're actually just reusing several bits of Java that you probably have already written code on today. We're trying to pre-compile the regex matcher so that it's a little bit more efficient. And down here in the body of the map, we're just taking a string, running a regex function on it, and looking at the output. The body of this is extremely boring, and that's actually an attribute, not a detriment to it. Very simple, very boring code in the body of this. The only part that's really even Hadoop specific is writing the output using its interfaces so that, again, we're abstracted from a physical file system, writing to the virtual interface instead so that it can direct it either to a large grid of disks or maybe even to the local disk if that was what was necessary. Now, the interesting part about this is, if you think about the efficiency of moving the data around for the original steps when we're trying to cull it down and try to minimize the set of data that we're working on, it makes a lot more sense to move the code around than it does to move the data around. This is the opposite of how we naturally write code as developers. We SQL select it and bring it down to the local machine, then we run through the pass. By writing just the Java functions, no special coding required, the Hadoop framework will send the compiled Java, the jar, the class files, across the network to the distributed nodes, running the code that we just authored right here on each of the nodes for the files that you want to participate in this large MapReduce job. The code going to the data nodes, not the opposite direction. That's a big deal. When you start talking about terabytes, you're bandwidth constrained. No matter how expensive a network you buy, you can't move terabytes across those lines, but you can move a couple KB of Java code with absolute ease. So the next step to this is adding a family of functions. And this is where Hadoop shines above MapReduce. You've got the basics of that, and you think, OK, that's cool. I can think about this. And there's other competitors in the MapReduce space. But the big differentiator is how many different components in a large distributed system eventually you find are necessary. I kind of need one of these, and I need one of these. Oh, I'm sorry. The other frameworks don't really help you with that. Hadoop is a family of products that goes far beyond what MapReduce just offers. At the very bottom is common, foundation to the whole Hadoop framework, and that offers that MapReduce functionality. But above and beyond that, just even a smattering, that's not the full list, we'll see the full list in just a second, is systems for managing large distributed transactions. Oh, we finished one MapReduce job, we can start another one on a set of the outputs. We can coordinate these transactions. Maybe we need some columnar storage, not quite a database, but something that looks at least like it has columns and rows that we can run selects on. That would be nice, especially at that same grand scale. It'd be nice if we also had a file system that kind of spanned this massive scale of terabytes as well. We might have to buy a SAN solution. No. That's covered by the Hadoop ecosystem. It's really very, very healthy in terms of the components that it offers. In fact, a table of all the bits, the most commonly used bits at least, are here. We've got column-oriented storage. We've got specific frameworks that even make it more efficient to deal with log file processing, harvesting IP addresses, occurrence, frequency of hits on a particular site or URL or destination. So there's layers of meaning above and beyond just the traditional MapReduce. That's almost too granular a level of coding for many of the solutions that we want to do on this large scale. And we've got this beautiful Hadoop file system. That is one of the key pieces that really makes all of this hang together. A distributed file system that we're going to tell you a little bit of the attributes about. Now, there's some principles that I think will make the rest of the presentation matter. These are what I want you to carry away as the ideas for why this talk should stick with you, why these ideas are very important in today's computing realm. With prices like this is last week's pricing on pricewatch.com. You can get 4 gig of RAM or a terabyte hard disk with a mail-in rebate, which we're horrible about on the USA, for $74.85. That's a vast difference in size. And that leads us to say that we really need to favor disk over memory. Economics just states that it's so. That's not a personal opinion. That's just a fact of the statistics right there. And in fact, on that same idea, why can't we take that a step further and say, I'd really like to buy cheap hardware instead of expensive hardware? Can you make this possible? Well, if we did that, we'd have a lot more downtime and a lot more outage. I mean, it's nice to go to a very reputable vendor and buy something with 5 nines or 6 nines of uptime and hot swappable this and that. And you'd be surprised to know that some of the big players say, we're not doing that anymore. In today's budget and today's economy, I'm not giving you $10,000 for the ultra-reliable server. I can buy 10 cheap boxes with the same CPU at the core for that same price. That's not a good use of my money. So the idea is to favor cheap hardware. And on that same line of thinking, we've got one last piece to add to the mix. If failure is inevitable, if you're buying cheap boxes, they're probably going to die and burn out, and the power supplies are going to go out a little bit more often. You need to build in the idea of redundancy and failover. You're not trying to buy your way out of failure, which is what buying that really expensive, hot swappable, redundant machine. You're buying the best you can so that it won't fail. On the opposite end, you want it in the software so that you can buy as cheap as possible. And really, Hadoop, through the file system, through the MapReduce, through the whole framework, is designed around the idea of hardware failures. In fact, to give you a tangible example, this is the Dalles, Oregon, northwest part of the United States. This is a Google data center. Notice it does not have a big logo on it. They do try to keep it pretty nonchalant. Facts say that they're having in this data center 3 to 7 machines die every single day. Now, how do we not just hear about people saying, oh, my Gmail account was hit by the latest data loss, so sorry, all my email's gone at that point, or I lost all my search engine results, or I lost all my Picasa albums at this point. The machine just goes on about its business, notices that one of the machines is dead, nominates another one to take its position, and then just keeps going through the motions with a new box, starting over any failed tasks, replicating any new data. In fact, the important thing to take away with the Hadoop framework being file system, transaction coordinating, and MapReduce, and database all in one, is that none of these attributes are written into our code. If you looked at the MapReduce that we had and we went through that small code example, none of these things are code that I wrote. And I've written plenty of systems in the past of my career that I've written retries and redundancy. If fail, if catch exception, go try and send it again. If I can't reach one of the servers, try another call, or maybe I'll have a nominated second failover IP address that I'll try it on. But that's not really code that you should be writing. No one really wants to pay you for that. That's just an unfortunate side effect of getting your job done with the core business logic that you're authoring. None of this stuff has to be authored in your MapReduce functions or your data processing with Hadoop. That is just an intrinsic part of the framework. There are configurable facets in which you can tune it to your preference, but configure, not necessarily need to write code. So what are some of the business realms that really make sense for Hadoop? Where have I seen it used that has been vastly successful over the course of the last year? There are some categories that really stand out. And in fact, let me separate these into the formal terms that we're hearing bandied about today in terms of data categorization. We've got the idea of highly structured data, and you know what? Databases are not dead and gone. We're still going to continue to buy great Oracle and IBM licenses for many years to come. This whole NoSQL movement and all of that, it did not replace databases. Even with the best implementations of Hadoop, it's not replacing them. These type of things still belong in a traditional database for fast, quick, select access. But we have two new categories that have kind of emerged. These did not take space away from the database. They added a new realm of data storage. That is kind of a column-oriented structure. Not formal database, not with relations, but columnar data structure. And we've got that in the form of maybe logs that we've parsed out to the IP address and the page that was hit, maybe the user cookie we also harvested out into 3 separate columns. But you know what? It's not structured with joins and relations that we actually want to set up. It's just kind of tabular, like a spreadsheet. Maybe on the far end, we have the files that we operated on just with the traditional documents. So like the idea of the traditional document where we're looking for the word inside it. That's not really structured at all. In fact, we don't know, other than it being a document, there's no sense of structure. It's just a jumble of words. So we've got some new categories of data that this can operate on. And the NoSQL movement, this thing that you're hearing a lot of buzz about, and I saw some other sessions that kind of cross into this NoSQL realm over the course of this week in this conference. NoSQL is not the death of the database, and in fact, the idea here is to work with a different scale of data than the traditional databases can. That's the reason for introducing these new tools. It solves an entirely different set of problems. So, where have I seen it used? I promised you a laundry list. These are the ones that I've physically had interaction with and seen it be vastly successful over the course of the last 12 months. Classification. Lots of use in the US government around our DC area. There's an enormous amount of companies just blossoming. There's a user group that gets 50 people to attend just for Hadoop-specific usage. That's amazing. We've got protein folding in the pharmaceutical industries. There was a company in Sweden I was just at a couple weeks ago that uses it for this very purpose. They've got a grid computing solution doing map and reduce on large quantities of protein calculations. And in fact, one in Colorado, believe it or not, is just documents. Spam filtering, the most boring job in the world that still makes money. The highest quality spam correctness we've ever seen in a product. And why? They don't try to do artificial intelligence. They, in fact, just look at billions of documents to get it right. Why not? Why start using artificial intelligence, which seems to always be off a little bit? Just look at a billion real spam messages in real time, updated every 24 hours. So piling in real time, updated every 24 hours on a Hadoop grid, and use those as the red flags for what's actually spam. kind of harvesting the human element here, people submitting what is spam and what's not. And for contextual ads, let me put this in terms of money for you. A contextual product thing, when you bring up Amazon or something like that and you say, oh, I recommend this product as well. You're looking at one product, you get a recommendation of another one. That type of select is never going to be allowed by any traditional DBA. If you think about what this looks like in kind of SQL pseudocode, this sub-select that's happening here is impossible. You can't do this across 1 million products or 1 million customers. It literally, for every person that's bringing up a product page, is just going to trash your database in terms of CPU and consumption. This is the kind of thing that is best calculated offline and then rendered into some sort of traditional database as a static reference. So Hadoop doing the background processing and calculation of what's a good recommended product for this one, then maybe storing it for a 24 or 12-hour period. And when the user interacts with the website, they're seeing that cached information from a traditional database. So it's selects like that that drive this big data MapReduce type of calculations. And in fact, making money on this was a very hard number to come by. I know there's probably some Amazon representatives in here, but that is a pretty impressive number. 30% of the sales affected by those recommendation applicabilities. Wow. Think if you could increase revenue, if you do any type of retail operation, think if you could increase that by 30%. You'd be a rock star if you could go to your boss and say, 30% improvement, can I have 2% of that? You'd be a rich person. We just heard the lecture about being a rock star. You would have a lot of money in your pocket if you could improve any business by 30% and take 2% of that. So HDFS, Hadoop file system, just a last mention, a light touch on each of these other players in the Hadoop ecosystem with the time that we have left. It's an open source implementation of, again, a Google paper. You see a trend here? Google writes the paper, someone else implements it into open source. This is cool. I like this. We got the smart guys coming up with the ideas there. And it's a replicated data store. So the idea being that you write a file in a normal, traditional Unix-like approach, and you actually get it replicated to as many other places as you'd like. You can tell it how many copies you want. You can tell it physically that I want one on this premise and one on another location, but it does not bleed into the code that you've written. HDFS is location aware, and you say, oh, that's a facet I don't want bleeding into my code. Yes, you do, because you probably want one hot copy local, and you probably, for a fire purpose or other natural disaster, want a second copy geographically some other location. So you can give it that preference of both local versus remote, and it knows to have a copy in both locations. If one of the copies disappears, the box just dies. It senses it about a minute or two later and starts making a second hot copy so that you've always got at least 2 on file. You've always got at least 2 copies at the ready. The Hadoop file system looks like a lot of the Unix commands that you can know and use today. CD, change group, rmdir, all the recursive functions that you operate on a Unix file system, very familiar. Then we have languages like Pig that bring the Hadoop processing concepts to non-programming audiences, maybe data analysts, maybe somebody who's a little bit less technical than the Java coders who are here at the seminar. But this is a value add brought on from Yahoo. It's really, really neat how much you can express in such a concise language. You can ask these big data questions like, should we, shouldn't we? And in fact, the example that I have here is a set of 1 million names. And let me actually show you what this looks like. Here's a Pig script. You can, again, this is not meant for programmers, it's meant more for data analysts, but it's getting you the same stuff as what we could write raw Java with. Look at this Pig sample. You can kind of Lex it. We've got a person. We're parsing from a CSV file. I'm doing an order by. I've got an ascending. I'm going to group and count how many names. I want to know how many Marys and Toms and Smiths and Pradeeps there are in this name list. Simple script like that. I'm running it against 1 million records. Simple script. It's dividing it and conquering it on the grid with very little intervention on my part. I didn't need to tell it how many nodes to run it on. It senses how many nodes are running on running Hadoop with configuration. It'll spread the job out to all of those. It'll move the data across the grid. It'll collate the result back onto one machine. You did not see that in the script that I wrote. Absolutely not. I did not write that into the script. It's part of the framework. 1 million rows collecting the names. And here's the output. counting the contents of that, I'm going to more the names, 1 million rows that quick. That's pretty impressive. Again, I didn't tell it how to scale. That's the part that impresses me the most. 2 other remaining things that are very interesting in the ecosystem. The one being the use of Hadoop on the Amazon cloud. Not just having raw machines, sure, we could set it up ourselves. But the important part being that they already have Hadoop machines running. You can instantiate these for literally pennies an hour. Pennies an hour. They have Hadoop machines on the ready, so if all of these ideas sound attractive to you, you can start experimenting without any hardware setup whatsoever. That is the cost. That's all it costs to run the Hadoop nodes. And they even have a wizard that can let you input those pig and JavaScripts through a web console. Now I joke, a wizard? Really? For developers? My grandma is not going to check out with a pig script, on Amazon. But at the same point, I'm still pretty impressed that they turned it even into a wizard form. That's how important usability is of this simplistic framework. They're doing the heavy work. They're supplying the machines. They're supplying the grid. Let's sum up what we've hopefully learned over the course of this quick summary on Hadoop. My thoughts are that this is really a new remapping of the Sapir-Whorf hypothesis. This was a study in the early 1900s that says language and the environment shape each other. And where I want to map this to is the fact that the ability to store this quantity of data will change whether you do. You might have come in here today saying, I don't really have that much data today, but I was a little bit interested in it. What I'd like to propose is the ability to store and operate on billions of rows will change maybe next Monday, whether you think you can. You might take on that project. You might try to make it work by the fact that you now know it's easy to do with a framework like this, whereas before you say, no, we're going to stick with our million rows. We're not going to step up to that next level. Final data point, and then we're closing. Do you know what this is? Final quiz, and then we're done. CERN popped up before I heard the answer. 15 petabytes of data retained each year. Hadoop being one of the tools they use to process that. Closing, end of processing parallelism has absolutely begun. Seeing how much work has gone into Hadoop proves this, and in fact, in the next couple of years, I think this statement's absolutely going to be true. I'd love to talk with you about Hadoop after the talk is over, but grab one of these books, study it further. I'm pretty excited. There's some real business happening around it. So thank you very much. I appreciate it.